Hello, dear friend, and welcome to the Sleepy Science Channel. Tonight, we're taking a journey beyond the atom and into the mysterious quantum realm, where everything we think we know about reality changes, and the seemingly impossible becomes possible. This isn't just a story about science, but an exploration of the limits of science itself. Now, let's begin. Imagine the world around you getting smaller, slowly shrinking beyond what even the most powerful microscopes can see. At this tiny scale, everything you thought was solid, the table, the air, even your own skin, is mostly empty space. Once, atoms were believed to be the smallest, indivisible pieces of everything, simple building blocks of the world. But as scientists looked closer, they discovered a hidden realm, the quantum world, where atoms and the particles within them behave in ways that defy our everyday experience. In this strange domain, certainty fades. Particles don't have exact positions or speeds. Instead, they exist as waves of possibility, dancing in probabilities and uncertainties. It's a universe ruled by chance and subtle rhythms, far from the solid objects we touch and see. What does it mean for something to be both particle and wave? How can something be in many places at once, or nowhere specific at all? These mysteries invite us to look deeper, to wonder about the invisible laws shaping all that exists. With this quiet curiosity, let's begin to explore the structure of the atom itself, tracing the path of discovery from early models to the revelations that opened the door to quantum mechanics. But long before modern science revealed these surprising truths, the idea of the atom began as a simple thought in ancient philosophy. Thousands of years ago, Greek thinkers imagined tiny, uncuttable pieces of matter, which they called atomos. These atoms were thought to be the smallest parts of the world, solid, indivisible, and eternal building blocks that made up everything we see around us. It was a bold idea, one meant to explain how the complex and changing world could be made from unchanging basic pieces. This ancient vision was less about experiment and more about imagination and reason. It was a way to bring order to the mysteries of nature, to find a foundation beneath the ever-shifting forms of life and matter. Yet these early atoms were nothing like the particles modern science would uncover. They were static and simple, not mysterious and strange. They lacked the layers of complexity that quantum physics would later reveal. With the advancement of scientific tools and experiments over centuries, scientists began to unravel what atoms really are. Instead of tiny, solid balls, atoms are made mostly of empty space, containing even smaller particles, electrons whirling in clouds around dense centers made of protons and neutrons. And these parts don't behave like solid objects. They move in waves, sometimes acting like particles, sometimes like waves of possibility. The transformation from ancient philosophy to modern quantum science is a remarkable story of how our understanding of the tiniest scales evolved. It teaches us that reality can be far more subtle and mysterious than first impressions suggest. The atom, once thought indivisible and simple, is a gateway to a universe filled with probabilities, uncertainties, and profound beauty, a universe waiting quietly beneath the surface of everything we know. In the early 19th century, the story of the atom took a new turn with John Dalton, a British scientist who brought fresh clarity to the idea of atoms. Dalton proposed that everything we see is made of tiny, indivisible particles called atoms, tiny spheres that combine in fixed ways to form different substances. This was a bold step toward modern chemistry, giving scientists a concrete framework to explain how matter behaves. Dalton's atomic theory suggested that atoms of a given element were identical in mass and properties, distinct from atoms of other elements. He imagined these atoms as solid, indivisible balls, each with its own weight and identity. Chemical reactions, in his view, were simply rearrangements of these atoms, combining and separating without breaking them apart. While his model was simple, it was powerful. Dalton's theory helped explain why substances combine in fixed proportions, why water is always 2 parts hydrogen and 1 part oxygen, for example. It laid the groundwork for understanding chemical reactions as the mixing and separating of atoms rather than mysterious transformations of matter. Yet, despite its usefulness, Dalton's vision had limitations. Atoms, it turned out, were not indivisible. Later discoveries revealed subatomic particles, electrons, protons, and neutrons, existing inside atoms, changing the very meaning of what an atom is. Still, Dalton's work marked a crucial moment in science. It bridged ancient philosophical ideas with experimental science, turning a centuries-old concept into a testable, predictive theory. His view of atoms as tiny, solid particles inspired generations of scientists to probe deeper, moving from indivisible spheres toward the strange quantum world beneath. This shift from simplicity to complexity mirrors the unfolding mystery of the atom itself, from solid blocks to dynamic systems, rich with unseen motion and uncertainty. At the end of the 19th century, the seemingly simple idea of the atom as a solid, indivisible sphere was challenged by new discoveries. J.J. Thomson, an English physicist, conducted experiments that revealed atoms were not as indivisible as once thought. In 1897, he discovered the electron, a tiny, negatively charged particle much smaller than an atom itself. Thomson's breakthrough came from studying cathode rays, streams of particles moving inside vacuum tubes. He found that these rays were made of particles lighter than any known atom, which he called electrons. This was the first glimpse into the complex inner world of the atom, proving it was made of smaller parts. The discovery of electrons meant atoms were not solid, indivisible units but contained internal structure. It raised new questions. If atoms have negative electrons, what balances their charge? How are these particles arranged inside the atom? Thomson proposed the plum pudding model, imagining the atom as a sphere of positive charge with electrons embedded like tiny raisins. Though this model was later replaced, it was a vital step in understanding atomic structure. Soon after, other subatomic particles were identified: protons, carrying positive charge, and neutrons, electrically neutral but contributing mass. These discoveries revealed the atom as a complex system, a miniature universe of charged particles interacting in delicate balance. This growing knowledge transformed chemistry and physics, showing that the building blocks of matter were themselves composed of parts, moving beyond the simplicity of Dalton's spheres. The atom was no longer a static object but a dynamic system, a mystery waiting to be unraveled. As we continue, we will explore how these early findings led scientists deeper into the strange, probabilistic world of quantum mechanics, where particles behave in ways that defy classical logic. Around 1909, Ernest Rutherford and his team set out to probe the internal structure of the atom with an ingenious experiment. They directed a beam of tiny, positively charged particles called alpha particles at an ultra-thin sheet of gold foil. According to the prevailing plum pudding model, these particles should have passed through almost straight, as the positive charge was thought to be spread evenly throughout the atom. What they observed, however, was astonishing. While most alpha particles did pass through with little or no deflection, a small fraction were deflected at sharp angles. Some even bounced back toward the source. This unexpected result suggested that the positive charge in the atom was not diffuse, but instead concentrated in a very small, dense region. Rutherford proposed a new model. The atom's positive charge, and nearly all its mass, reside in a tiny nucleus at the center. The electrons orbit this nucleus, much like planets orbiting a sun, but on an unimaginably smaller scale. This nuclear model overturned the plum pudding idea and introduced a whole new way of understanding atomic structure. The discovery of the nucleus explained why most alpha particles pass through unaffected. The atom is mostly empty space. It also introduced questions about how electrons remain stable around the nucleus, which classical physics struggled to answer. Rutherford's experiment was a pivotal moment, marking the birth of modern atomic physics. It revealed a hidden, dense core within matter, and set the stage for the quantum mechanical revolution that would soon follow, where certainty gave way to probability, and the familiar rules of the visible world no longer applied. This glimpse into the atom's heart invites us to keep looking closer, deeper, and softer into the world's smallest and most mysterious building blocks. Building on Rutherford's discovery of the nucleus, Niels Bohr introduced a new vision of atomic structure in 1913. His model proposed that electrons do not simply orbit the nucleus randomly, but move in specific stable paths or shells, somewhat like planets circling the sun. This idea was revolutionary because it introduced the concept of quantized energy levels. Electrons could only occupy certain allowed orbits without radiating energy and spiraling into the nucleus. Bohr suggested that electrons jump between these fixed orbits by absorbing or emitting discrete packets of energy called quanta. This explained the distinct lines observed in atomic spectra, patterns of light emitted or absorbed by elements. Each line corresponded to a specific electron transition between energy levels. While Bohr's model worked beautifully for hydrogen, the simplest atom, it struggled to explain the behavior of more complex atoms. Nonetheless, it marked an important step toward quantum theory by blending classical ideas with new quantum rules. The planetary analogy provided a comforting image, electrons circling the nucleus in neat orbits. But the true quantum world would prove to be far more mysterious and less visual. Still, Bohr's insights paved the way for later developments, including wave mechanics and the probabilistic interpretation of electron behavior. Bohr's model also hinted at a deeper principle, that nature's smallest parts don't follow continuous classical motions, but move in discrete steps governed by fundamental constants. This was a profound shift from the classical worldview, inviting us to reconsider the very nature of matter and energy. With Bohr's planetary atom, the door to quantum mechanics opened wider, beckoning us to explore the subtle, strange dance of particles at the heart of all things. Bohr's planetary model was a groundbreaking step, but it soon became clear that the classical physics of the 19th century couldn't fully explain the strange behavior observed at atomic and subatomic scales. As experiments delved deeper into the quantum realm, scientists encountered phenomena that defied the familiar rules of motion, energy, and measurement. One early challenge was the photoelectric effect, where light shining on certain metals ejects electrons. Classical wave theories of light predicted a gradual energy increase, but experiments showed electrons were emitted only when the light reached a specific frequency, suggesting that light behaved like discrete packets of energy, or quanta. This insight, introduced by Albert Einstein in 1905, helped launch quantum theory. Around the same time, Max Planck proposed that energy is quantized, emitted or absorbed in fixed amounts, to explain how hot objects radiate light. These ideas shattered the classical notion that energy changes were smooth and continuous. Then came the unsettling wave-particle duality, where particles like electrons exhibited properties of both waves and particles. Louis de Broglie suggested electrons have valve-like nature, and experiments confirmed this, showing interference patterns typical of waves. This duality undermined the classical picture of particles as tiny billiard balls moving predictably. Werner Heisenberg's uncertainty principle further challenged classical determinism. It revealed fundamental limits on how precisely we can know certain pairs of properties, like position and momentum, at the same time. This uncertainty is not due to measurement flaws, but is an intrinsic feature of nature. These developments culminated in the creation of quantum mechanics, a mathematical framework describing probabilities and uncertainties rather than fixed trajectories. Classical physics gave way to a world where observation, chance, and wave functions govern the tiniest scales. This new quantum view unsettled many, but it also opened a window into the deep structure of reality, inviting us to reconsider what it means to truly know the universe. Let's pause here and explore one of the most intriguing and fundamental concepts in quantum mechanics: wave-particle duality. At the heart of the quantum world lies a surprising truth. Entities like electrons and photons don't fit neatly into classical categories. Sometimes they behave like particles, small and localized. Other times they act like waves, spreading out and interfering with themselves. This dual nature was first glimpsed in experiments with light. For centuries, light was considered a wave, responsible for phenomena like diffraction and interference patterns. Yet, the photoelectric effect revealed that light also behaves like a stream of particles, quanta of energy called photons, each carrying a specific amount of energy. The concept took a bold leap when Louis de Broglie proposed in 1924 that not just light, but all matter, including electrons, could exhibit wave-like properties. This idea was revolutionary. It suggested that tiny particles might have an associated wavelength, influencing how they move and interact. Experiments soon confirmed this duality. In electron diffraction experiments, electrons fired through thin crystals produced interference patterns, signatures of wave behavior, something unimaginable if they were simply tiny solid particles. Wave-particle duality challenges our classical intuitions. How can something be both a particle and a wave? The answer lies in the probabilistic nature of quantum mechanics. Instead of having definite positions and velocities, particles are described by wave functions, mathematical expressions encoding the probabilities of finding them in various places. This dual behavior isn't just a curiosity, it lies at the core of quantum technology. From electron microscopes to semiconductors and lasers, understanding wave-particle duality allows us to manipulate the quantum world in ways that power modern life. As we continue, we'll explore how this duality shapes atomic structure and the mysterious rules governing the tiniest parts of reality. One of the most striking demonstrations of wave-particle duality is the famous double-slit experiment, which has captivated physicists for over a century. In this experiment, a beam of light, or even particles such as electrons, is directed towards a barrier containing two very narrow, closely spaced slits. Behind this barrier, a detection screen records where the light or particles land. If particles behaved like tiny solid bullets, we would expect to see two bright spots on the screen, corresponding exactly to the two slits. But instead, what appears is a series of alternating bright and dark bands, known as an interference pattern. This pattern is a clear signature of wave behavior, created when waves overlap and interfere, amplifying in some places and cancelling out in others. What makes this experiment truly astonishing is what happens when particles are sent through the slits one at a time, slowly building up the pattern over time. Each particle arrives as a single point on the screen, like a localized particle. Yet, as more and more particles pass through, the interference pattern emerges as if each particle somehow passed through both slits simultaneously and interfered with itself, behaving like a wave, not a tiny ball. When detectors are placed to measure which slit each particle passes through, this wave-like behavior disappears. Instead, particles behave as if they took one path or the other, and the interferent pattern vanishes. This suggests that the very act of observation changes the nature of what is observed, a profound insight into the quantum world. The double-slit experiment forces us to rethink basic assumptions about reality. It reveals that at the quantum level, particles do not have definite paths or positions until they are measured. Instead, they exist as wave functions, mathematical descriptions of probabilities spread over space. When measured, the wave function collapses to a definite location. This experiment shattered classical notions of certainty and locality. It remains one of the most profound and elegant illustrations of quantum mechanics, a reminder that the universe at its smallest scales is far stranger and more mysterious than our everyday experience suggests. In the quantum world, there are fundamental limits to what we can know simultaneously about certain properties of particles. This is captured in Heisenberg's uncertainty principle, a cornerstone of quantum mechanics. It tells us that the more precisely we try to measure a particle's position, the less precisely we can know its momentum, and vice versa. This isn't due to flaws in our instruments, but a fundamental property of nature itself. Imagine trying to pinpoint exactly where an electron is. The act of measuring its position with great accuracy inherently disturbs the electron's momentum, making it impossible to know both precisely at the same time. This isn't just a technical limitation. It reflects the inherent fuzziness of particles at microscopic scales. This principle challenges classical ideas where objects have definite, predictable positions and velocities. Instead, at the quantum level, particles behave in ways that resist exact description, embracing probability and uncertainty. It reminds us that reality is not a simple clockwork mechanism, but a dance of possibilities. Heisenberg's uncertainty principle has profound implications. It means that the universe itself has a built-in limit to predictability, setting a boundary for the exactness of measurement and knowledge. This uncertainty is not just theoretical. It influences how atoms bond, how particles interact, and underpins the stability of matter. Understanding these limits helps explain why the quantum world feels so strange and counterintuitive, yet also why it is so rich and full of surprising phenomena. It invites us to accept a universe where certainty is replaced by possibility, and where the act of observation plays a central role in shaping what we know. One of the most important tools for understanding the quantum world is Schrödinger's wave equation. Developed by Erwin Schrödinger in the 1920s, this mathematical equation describes how the quantum state of a particle, such as an electron, changes over time. Rather than picturing electrons as tiny billiard balls moving along fixed paths, Schrödinger's equation treats them as waves that spread out and interfere, creating patterns of probability. These probabilities are not just abstract ideas. They form what we call probability clouds or orbitals, regions around an atom's nucleus where the electron is most likely to be found. Unlike the precise orbits in classical models, these clouds give a fuzzy, ever-changing shape to where electrons can exist, reflecting the uncertainty and fluidity of the quantum realm. Instead of saying, "the electron is here," quantum mechanics tells us it's more accurate to say, "the electron has this likelihood of being here." Schrödinger's equation helps calculate these likelihoods, revealing the complex and beautiful shapes that electrons inhabit. This concept fundamentally changes how we understand matter's building blocks. Atoms aren't tiny solar systems, but rather dynamic, probabilistic systems, where electrons blur in space, guided by the mathematics of waves. The wave equation connects the unseen quantum behavior with measurable properties, making it central to modern physics and chemistry. By imagining electrons as probability clouds, We embrace a world where certainty gives way to possibility, a quiet dance of existence that defies everyday intuition, yet shapes everything we see around us. In quantum mechanics, the idea of a quantum state is fundamental. It describes all the information we can know about a particle or system at a given moment. But unlike in classical physics, where an object has a definite position or speed, a quantum state allows for something far more mysterious: superposition. Superposition means that a particle can exist in multiple possible states at once. For example, an electron might be in a blend of different locations or energies simultaneously, not one or the other, but both at once. It's only when we measure or observe the particle that this blend collapses into a single outcome. This concept challenges our everyday experience. We're used to things being in one place or having one property, but at the quantum scale, particles seem to hold several possibilities together, woven into a single quantum state. It's as if reality itself holds its options open until we take a closer look. Superposition is key to many quantum phenomena and technologies, from the strange interference patterns we discussed earlier to the emerging field of quantum computing, where bits can represent both 0 and 1 wa simultaneously. Embracing superposition invites us to see the quantum world not as fixed and certain, but as a realm of possibilities, softly balanced in delicate harmony until observed. Quantum entanglement is one of the most puzzling and fascinating phenomena in the quantum world. When two particles become entangled, their properties become linked in such a way that the state of one instantly influences the state of the other, no matter how far apart they are. This connection persists even if they are separated by vast distances, a phenomenon Albert Einstein famously called spooky action at a distance. Imagine two entangled particles as twins sharing a secret. Measure a property of one twin, and you immediately know the corresponding property of the other, even if it's on the other side of the universe. This instantaneous connection seems to defy the classical idea that information can only travel at the speed of light. Entanglement challenges our intuition about space and time. It reveals a deep, underlying unity between particles that transcends ordinary physical separation. Scientists have tested entanglement extensively, confirming that it is a real and fundamental aspect of nature. Beyond its mysteries, entanglement is the foundation for emerging quantum technologies, like quantum computing and ultra-secure communication, where the unique links between particles can be harnessed to process and transmit information in entirely new ways. This strange, invisible bond reminds us that the quantum realm operates with rules far different from our everyday world, a realm where distance and separation lose their usual meaning. The ideas emerging from quantum experiments didn't just add details to existing physics, they upended the very foundations of how we understood reality. Classical physics, built on the certainty of Newton's laws and the predictability of particles moving in defined paths, suddenly seemed incomplete. Quantum mechanics introduced uncertainty, probabilities, and dual natures, showing that at the smallest scales, the world behaves in ways that defy everyday logic. Particles aren't tiny billiard balls, but waves of possibility, and measurement itself changes the outcome. This shift challenged the long-held belief that the universe operates like a well-oiled machine with exact, knowable laws. Instead, quantum physics revealed a universe more mysterious, where chance plays a fundamental role. The classical world still holds true for our daily experience, but beneath it lies a subtle, probabilistic reality. This quantum revolution reshaped physics, philosophy, and technology, paving the way for innovations like semiconductors, lasers, and quantum computing. Understanding how these ideas transformed science invites us to appreciate the delicate balance between order and uncertainty at the heart of the universe. Beneath the familiar layers of atoms lies an even more fundamental realm, composed of tiny particles that form the very essence of matter and energy. These fundamental particles are not made of anything smaller. They represent the most basic building blocks that physics has discovered so far. Scientists categorize them mainly into two groups: fermions, which constitute matter itself, and bosons, which act as carriers for the forces that govern interactions among particles. Fermions include quarks and leptons. Quarks are especially important because they combine in groups of three to form protons and neutrons, the particles that cluster together to create atomic nuclei. Without quarks, atoms as we know them would not exist. Leptons, on the other hand, include electrons, the negatively charged particles that orbit around these nuclei, creating the structure of atoms. There are also neutrinos, tiny, nearly massless leptons that rarely interact with matter, passing through us and the Earth in vast numbers every second, almost unnoticed. Each fundamental particle exists in several varieties or flavors, each with unique masses, charges, and properties that influence how they behave. These subtle differences determine how particles interact and combine to build the diverse matter that makes up everything from dust to stars. Opposite to fermions, bosons are the force carriers that mediate fundamental interactions in the universe. Photons carry the electromagnetic force, allowing electricity, magnetism, and light to exist and propagate. Gluons are the particles responsible for the strong nuclear force, a powerful glue that holds quarks tightly bound inside protons and neutrons, giving atomic nuclei their stability. The W and Z bosons mediate the weak nuclear force, which governs processes like radioactive decay and nuclear fusion in stars. Among these bosons, the Higgs boson holds a special place. Discovered only recently in 2012, it interacts with the Higgs field, which imparts mass to other particles, making it fundamental to the formation of the universe's structure. All these particles and forces fit within the framework of the Standard Model of particle physics. This framework is a mathematical and conceptual structure that organizes the particles into families, describing how they interact and combine to build the complex world we experience. The Standard Model has been tested extensively in experiments and has predicted many phenomena with astonishing accuracy. However, the Standard Model is not the final answer. It notably excludes gravity, the force that shapes planets, stars, and galaxies, and cannot explain dark matter, the mysterious substance thought to comprise most of the universe's mass, yet remaining invisible to current instruments. Scientists continue to search for theories that unify these gaps, hoping to reveal even deeper layers of reality. Despite its limitations, the Standard Model offers a remarkable glimpse into the quiet order underlying the universe's apparent complexity. It shows us how the tiniest particles, governed by subtle forces, come together in intricate harmony to create everything from your own body to distant galaxies. This profound understanding enriches our view of the quantum world, highlighting the delicate balance and structure within all things, seen and unseen. Beneath the particles themselves lies another profound layer of nature's design, the fundamental forces. These invisible threads weave the universe together, governing how matter interacts, moves, and changes. There are 4 known fundamental forces, each with its own role and reach. First is the electromagnetic force, perhaps the most familiar. It controls how charged particles like electrons and protons attract or repel each other. This force is behind electricity, magnetism, and light, shaping everything from the glow of a candle to the workings of your own nervous system. It acts over infinite distances but grows weaker with separation. Next is the strong nuclear force, a powerful but very short-range force that holds quarks tightly bound inside protons and neutrons. This force also glues these particles together within the atomic nucleus, overcoming the repulsion between positively charged protons. Without the strong force, atoms would not hold together, and matter as we know it would not exist. Then comes the weak nuclear force, responsible for subtle but vital processes, like radioactive decay and nuclear fusion in stars. Though its name suggests weakness, this force plays a crucial role in the life cycle of stars and the creation of elements essential for life. Lastly, gravity governs the large-scale structure of the universe. It is the force of attraction between masses, shaping the motion of planets, stars, and galaxies. Though weakest of the four, gravity's influence extends infinitely and accumulates over vast distances, sculpting the cosmos. Together, these four forces form the foundation of physical reality. They govern everything from the tiniest particles dancing in atoms to the majestic motions of galaxies swirling through space. Understanding these forces is key to unlocking the secrets of the quantum world and beyond. Among the fundamental particles and forces, one discovery stands out for its mysterious and essential role: the Higgs boson. Often called the God particle. Though the nickname oversimplifies its significance, the Higgs boson reveals how particles gain mass, the very property that gives them weight and presence in our world. The story begins with the question: why do some particles have mass while others, like photons of light, do not? Physicists theorized the existence of a pervasive field filling all space, the Higgs field. As particles move through this field, they interact with it to varying degrees. This interaction slows them down and endows them with mass, much like how moving through a thick syrup would impede a swimmer's motion. The Higgs boson is a ripple, or excitation in this field, a particle that emerged from the field's energy. It was finally observed in 2012 at the Large Hadron Collider, confirming decades of theoretical work and filling a crucial gap in the standard model of particle physics. Without the Higgs mechanism, particles would remain massless, zipping through space at the speed of light, unable to form atoms, molecules, or the structures that compose stars, planets, and living beings. It's this invisible, subtle presence that makes the material universe possible. The discovery of the Higgs boson was a milestone, deepening our understanding of the quantum world's fabric. It reminds us how unseen forces and fields shape reality, working quietly behind the scenes to give form and substance to everything we experience. Beneath the particles we see in experiments lies a deeper reality, the world of quantum fields. Rather than thinking of particles as tiny billiard balls, modern physics reveals that every type of particle is actually a ripple or excitation in a corresponding quantum field that fills all of space. Imagine space as a vast, invisible ocean, with waves rising and falling across its endless surface. Each wave corresponds to a particle, an electron here, a photon there, appearing when the field is excited. These fields exist everywhere, even in the emptiest parts of the universe, quietly vibrating and interacting. This idea transforms our understanding of matter and energy. Particles aren't isolated points, but manifestations of underlying fields, constantly shifting and fluctuating. Sometimes particles pop into existence briefly before disappearing, a phenomenon known as quantum fluctuations. Quantum field theory combines quantum mechanics and special relativity, providing the framework for the standard model and our most precise descriptions of particle interactions. It explains how forces are carried by particles like photons and gluons, which themselves are excitations in force fields. The fields are interconnected, dancing together in complex ways that give rise to the rich tapestry of particles and forces shaping the universe. Even empty space has energy, sometimes called vacuum energy, which influences cosmic phenomena like the universe's expansion. Understanding quantum fields opens a window into the silent, dynamic fabric beneath all matter. It shows that reality is more than solid objects. It is a continuous, energetic web of possibilities and interactions, humming gently beneath the surface of everything we know. Even the quiet emptiness of space is never truly empty. According to quantum field theory, the vacuum, what we might think of as nothing, is actually a bubbling sea of activity. Tiny, short-lived disturbances called virtual particles constantly appear and vanish, flickering in and out of existence in the blink of an eye. These virtual particles are not particles in the usual sense. They cannot be directly observed or captured. Instead, they are temporary ripples in quantum fields, born from the uncertainty inherent in the quantum world. Their brief lives and rapid disappearances are allowed by the Heisenberg uncertainty principle, which permits certain fluctuations in energy and time. Vacuum fluctuations, as these processes are called, contribute to subtle effects measurable in experiments. For example, the Casimir effect demonstrates how two metal plates placed very close together in a vacuum experience a tiny force pushing them together, caused by the altered distribution of virtual particles between the plates. Virtual particles also play a vital role in the forces between real particles. They act as intermediaries, popping in and out to carry forces like electromagnetism and the strong nuclear force. When two charged particles repel or attract, it's as if they exchange a cloud of virtual photons, though these photons never exist long enough to be detected. These ephemeral entities reveal a universe far more dynamic than our everyday experience suggests. The vacuum is alive with hidden energy and restless motion, reminding us that beneath the calm surface of reality lies a restless, vibrant quantum dance. This strange, invisible activity underpins much of the quantum world, deepening the mystery and wonder of the universe's smallest scales. Despite the elegance and success of the standard model, it leaves many deep questions unanswered. Physicists know it is incomplete, like a map that captures familiar landscapes but misses hidden continents waiting to be explored. One of the biggest mysteries is dark matter, an invisible substance that makes up most of the universe's mass but cannot be explained by any known particle in the standard model. Alongside dark matter, dark energy remains even more puzzling. It is the mysterious force driving the accelerated expansion of the universe, a phenomenon that challenges our understanding of gravity and the fabric of space-time itself. Neither dark matter nor dark energy fit neatly into the existing framework, hinting at new physics beyond our current theories. Another puzzle lies in the nature of gravity. Unlike the other fundamental forces, gravity resists integration into the quantum world. The standard model does not include a quantum theory of gravity, and efforts to unify it with the other forces, such as string theory or loop quantum gravity, remain incomplete and speculative. Physicists also grapple with why the parameters of the standard model, particle masses, force strengths, and more, take the values they do. Are these values fundamental constants of nature, or do they vary in unseen ways across the universe or multiple universes? Experiments of particle colliders continue to search for signs of new particles or forces that could extend the standard model. The Large Hadron Collider, for instance, probes energies and scales that might reveal clues to these deeper mysteries. These ongoing questions reflect the vibrant frontier of physics, where the known meets the unknown. They invite us to wonder and imagine, as science quietly pushes the boundaries of what we understand about the universe's smallest, most fundamental building blocks. Quantum tunneling is a remarkable phenomenon where particles pass through barriers that, according to classical physics, should be impossible to cross. Imagine a tiny particle approaching a wall that it does not have enough energy to climb over. Instead of bouncing back, the particle sometimes appears on the other side, as if it has slipped right through. This defies our everyday experience, but is a fundamental aspect of quantum mechanics. At the heart of tunneling lies the wave nature of particles. Each particle is described by a wave function, which extends beyond physical boundaries. This wave function doesn't abruptly end at a barrier, but fades gradually, allowing a small probability that the particle can be found on the other side. It's a delicate balance between the particle's energy and the thickness and height of the barrier. Quantum tunneling is not just a theoretical curiosity. It plays a crucial role in many natural and technological processes. In the sun's core, tunneling allows hydrogen nuclei to overcome their mutual repulsion and fuse together, releasing the energy that powers the stars and provides warmth and light to our planet. In everyday technology, tunneling underpins the function of devices like the scanning tunneling microscope, which images surfaces at the atomic scale by detecting tunneling electrons. It also enables tunnel diodes used in high-speed electronics and is essential in the operation of flash memory in computers and smartphones, where electrons tunnel through insulating barriers to store data. These applications reveal how the mysterious quantum world quietly shapes the tools we use and the stars we gaze upon. Quantum tunneling teaches us that nature's rules can be stranger and more fascinating than we imagine, and that tiny particles hold the keys to both cosmic power and advanced technology. Superposition is a core principle of quantum mechanics that allows particles to exist in multiple states at once. Imagine a coin spinning in the air. It is neither heads nor tails, but holds the possibility of being both until it lands. In the quantum world, particles like electrons or photons can exist in a blend of different states simultaneously, described mathematically by a wave function. This seemingly strange property becomes especially powerful in quantum computing. Unlike classical computers, which use bits represented by either 0 or 1, quantum computers use quantum bits, or qubits, that can be both 0 and 1 at the same time, thanks to superposition. This allows a quantum computer to process a vast number of possibilities all at once, opening the door to solving complex problems much faster than traditional machines. Superposition also leads to quantum parallelism, where calculations are performed simultaneously across many states. This capability could revolutionize fields like cryptography, materials science, and optimization, enabling tasks that classical computers would find impossible within any reasonable time. Yet, superposition is delicate. It can be disrupted by interactions with the environment, a process called decoherence, which forces the system to choose a definite state and collapse its multiple possibilities. This fragility makes building practical quantum computers a significant challenge. Researchers are developing ways to protect and control superposition, using techniques such as error correction and quantum entanglement, which links qubits together in complex ways. Together, these principles form the foundation of quantum information science, promising a new era where the quantum world's mysterious features become tools for technology. As we explore further, we'll see how superposition intertwines with entanglement and measurement to create the unique power of quantum computing. Quantum cryptography is an exciting application of quantum mechanics that promises fundamentally secure communication. Traditional encryption methods rely on complex mathematical problems to protect data, but advances in computing threaten to break these codes. Quantum cryptography, however, uses the unique properties of quantum particles to guarantee security in a way that classical systems cannot match. At the heart of quantum cryptography is the principle that measuring a quantum system inevitably disturbs it. This means any attempt by an eavesdropper to intercept a quantum communication will leave detectable traces, alerting the communicating parties to the intrusion. This idea is harnessed in protocols like quantum key distribution, or QKD, which allows two parties to share a secret encryption key with absolute security. QKD uses particles of light called photons, transmitted over optical fibers or through the air. These photons are prepared in special quantum states, often involving polarization or phase. Because of quantum superposition and entanglement, the security of the key exchange is guaranteed by the laws of physics rather than assumptions about computational difficulty. Beyond just theory, quantum cryptography is already moving into practical use. Some cities have established secure quantum communication networks, and ongoing research aims to extend this security over long distances and satellite links. This development could protect sensitive information in fields such as finance, government, and healthcare. While still early in its technological maturity, quantum cryptography points towards a future where privacy and security are woven into the fabric of communication itself, protected by the profound Gamma. Mysteries of the quantum world. As we continue, we'll explore how these quantum principles open doors to new technologies and deeper understandings of reality. Bose-Einstein condensates are a remarkable state of matter that emerges when particles called bosons are cooled to temperatures near absolute zero, just a fraction of a degree above the coldest possible bar. Temperature. At these ultra-low temperatures, individual particles lose their distinct identities and begin to behave as a single quantum entity, occupying the same lowest energy state. This strange and beautiful state was predicted by Albert Einstein and Satyendra Nath Bose in the early 20th century, but was only realized experimentally in the 1990 AZ. Creating a Bose-Einstein condensate requires complex cooling techniques, using lasers and magnetic fields to slow atoms almost to a standstill. What makes these condensates fascinating is how they reveal quantum phenomena on a scale visible to the naked eye. Unlike ordinary gases or solids, the particles in a condensate move in unison, exhibiting wave-like properties that overlap perfectly. This collective behavior leads to unusual effects, such as superfluidity, the ability to flow without friction, and coherence, where particles act in harmony. Bose-Einstein condensates provide a unique window into quantum mechanics, allowing scientists to study behaviors normally hidden in the microscopic world. They also help us understand other exotic states, such as superconductors, where electrical resistance disappears, and new materials with unusual magnetic or optical properties. Beyond pure research, these condensates could lead to advances in precision measurement, quantum simulations, and even quantum computing. By manipulating these new states of matter, physicists are probing the boundaries between the classical world we live in and the quantum world that governs the very small. This exploration of quantum states continues to deepen our understanding of nature's subtle complexity, unveiling fresh mysteries with every experiment. Quantum sensors represent a new frontier in measurement technology, harnessing the unique properties of quantum mechanics to achieve levels of precision far beyond what classical devices can manage. These sensors exploit phenomena like superposition, entanglement, and quantum coherence to detect extremely subtle changes in physical quantities such as magnetic fields, gravity, and time. At their core, quantum sensors use quantum states that are exquisitely sensitive to their environment. For example, atomic clocks, a type of quantum sensor, measure time with astonishing accuracy by tracking the vibrations of atoms at specific energy levels. These clocks are so precise they lose less than a second over millions of years, forming the backbone of technologies like GPS and telecommunications. Another powerful example is magnetometers based on quantum principles, which can detect minute magnetic fields with unprecedented sensitivity. This capability has transformative applications in medicine, such as magnetoencephalography, which maps brain activity, by measuring magnetic fields produced by neurons. Similarly, quantum sensors are being developed to detect gravitational waves, subtle ripples in space-time caused by cosmic events like black hole mergers. What sets quantum sensors apart is their ability to measure with minimal disturbance to the system being observed, thanks to their quantum coherence. This reduces noise and errors that typically limit classical sensors, enabling breakthroughs in fundamental physics experiments and practical technologies alike. As quantum sensing technology advances, it promises to revolutionize fields ranging from navigation and mineral exploration to environmental monitoring and national security. By leveraging the delicate features of the quantum world, these sensors reveal details about our universe that were previously hidden or impossible to measure. Quantum sensors embody the subtle interplay between fundamental science and real-world impact, quietly enhancing our ability to observe and understand the cosmos with astonishing clarity. Quantum coherence is the delicate condition that allows quantum systems to exist in superposition states, where particles can simultaneously hold multiple possibilities. It is the foundation for many quantum technologies, including quantum computing and sensing. When a quantum system is coherent, its wave-like properties remain intact, enabling interference effects and entanglement that classical systems cannot replicate. However, maintaining coherence is a profound challenge. Quantum systems are extremely sensitive to their environments. Tiny interactions with surrounding particles, stray electromagnetic fields, or even temperature fluctuations can cause decoherence, a process where the fragile quantum states lose their coherence and behave more classically. This transition effectively destroys the quantum information, collapsing the superposition into a single, definite state. Decoherence poses a major obstacle in developing reliable quantum technologies. For example, quantum computers require sustained coherence in their qubits to perform complex calculations. Any loss of coherence leads to errors and limits the time over which quantum information can be preserved. Scientists must engineer carefully controlled environments, often near absolute zero temperatures, to shield quantum systems from noise and disturbances. Understanding decoherence is also central to foundational questions about quantum mechanics itself. It explains why we do not observe quantum superpositions in everyday objects. The environment constantly measures and collapses these states, producing the classical world we experience. Research is ongoing to find materials and techniques that prolong coherence times, such as topological quantum states, or error-correcting codes that protect quantum information. Advances in this area could unlock practical quantum technologies and deepen our grasp of nature's underlying rules. Quantum coherence and decoherence reveal the delicate balance at the heart of the quantum realm, a world where information is both fragile and powerful, shaping the future of science and technology. Quantum science is quietly transforming the future of technology in ways that may seem almost magical. At its core, quantum mechanics reveals a world where information behaves differently, where particles can exist in multiple states at once, become linked across distances, and tunnel through barriers. Harnessing these properties is opening new frontiers for innovation. Quantum computing promises to revolutionize how we solve complex problems. Unlike classical computers, which process bits as zeros or ones, quantum computers use qubits that exploit superposition and entanglement. This enables them to perform many calculations simultaneously, potentially cracking codes, optimizing logistics, or simulating molecular processes far beyond classical capabilities. Though still in early stages, these machines could reshape industries from medicine to finance. Quantum cryptography offers unprecedented security. By using quantum states to encode information, it becomes theoretically impossible to intercept messages without detection. This unhackable communication could protect sensitive data, from personal privacy to national security, in an increasingly connected world. Quantum sensors enhance precision in ways classical tools cannot match. They can detect tiny changes in magnetic and gravitational fields, enabling advances in navigation, medical imaging, and environmental monitoring. These sensors might allow explorers to map underground structures or doctors to diagnose diseases earlier. Research into new quantum materials and phenomena, like Bose-Einstein condensates, could unlock exotic states of matter with unique properties useful for technology and fundamental science. Despite challenges, quantum science's steady progress hints at a future where technology not only grows more powerful, but more intimately linked to the subtle laws of the universe. As these advances unfold quietly behind the scenes, they promise to reshape our world in profound, gentle ways, much like the soft, hidden dance of particles we've been exploring tonight. Quantum mechanics doesn't just describe how particles behave, it also invites deep questions about what that behavior means. Scientists have developed different interpretations to make sense of the strange quantum world, each offering its own view of reality. One of the earliest and most widely taught is the Copenhagen interpretation. It suggests that particles exist in a state of probability, described by a wave function, until they are observed. At that moment, the wave function collapses, and the particle takes on a definite position or state. This idea embraces uncertainty as a fundamental aspect of nature, rather than a limitation of measurement. In contrast, the many worlds interpretation proposes a vastly different picture. Instead of a single reality, it suggests that every possible outcome of a quantum event actually occurs, each in its own branching universe. Every time a measurement is made, the universe splits into multiple versions, where all possibilities unfold simultaneously. This view removes the need for wave function collapse, but introduces an almost unimaginable multitude of parallel realities. Other interpretations include pilot wave theory, which posits hidden variables guiding particles, and relational quantum mechanics, which sees quantum states as dependent on the observer's perspective. These interpretations do not change the mathematical predictions of quantum mechanics, but they reflect how scientists attempt to understand the underlying nature of reality. Each one invites us to consider profound philosophical questions about observation, existence, and the fabric of the cosmos. Though these ideas might seem abstract, they reveal how quantum mechanics challenges not only our scientific understanding, but also our deepest assumptions about the world. As we gently explore these views, we uncover layers of mystery still waiting to be fully understood. One of the most puzzling questions in quantum mechanics is called the measurement problem. It asks, how does the act of measuring a quantum system cause it to change from a blur of possibilities into a single, definite outcome? Before measurement, particles exist in a superposition, a combination of all possible states at once, described mathematically by a wave function. But when we observe or measure them, this wave function seems to collapse, and we see just one specific result. This sudden collapse isn't explained by the usual equations of quantum mechanics, which describe smooth, continuous evolution of the wave function. Instead, collapse appears to be an abrupt and somewhat mysterious event. Why and how this happens remains a deep question, sparking many interpretations and debates among physicists. Some interpretations, like the Copenhagen view, accept collapse as a fundamental part of measurement, where observation causes reality to choose a definite state. Others, like the many worlds interpretation, avoid collapse entirely, proposing that all possible outcomes happen in branching parallel universes, and our experience is just one thread of that vast tapestry. Scientists have also proposed alternative ideas, including spontaneous collapse theories, which suggest collapse happens randomly, even without observation, but with a very low probability. Another approach involves decoherence, where interaction with the environment causes quantum states to appear classical, effectively hiding the superpositions from view without requiring true collapse. The measurement problem touches on the limits of our understanding and the deep interplay between observation and reality. It reveals how, at the smallest scales, the universe challenges our everyday intuitions about how things exist and change. As we rest in this quiet mystery, the measurement problem reminds us that some questions in science remain beautifully open, inviting gentle curiosity rather than immediate answers. Quantum mechanics challenges the way we think about reality itself, especially when it comes to the role of the observer. In classical physics, objects exist in definite states whether or not anyone is watching. But in the quantum world, observation takes on a mysterious and fundamental role. It seems that what we measure can influence the outcome, blurring the line between observer and observed. This idea traces back to the early days of quantum theory, where experiments showed that particles don't have fixed properties independent of measurement. Instead, their characteristics, like position or momentum, become defined only when observed. Before that, they exist as probabilities spread across many possibilities. Some interpretations suggest the observer's consciousness causes the wave function to collapse, deciding the fate of the quantum system. This consciousness causes collapse idea remains controversial, and many physicists prefer to keep the observer as simply any interaction that extracts information, not necessarily requiring a conscious mind. Others argue that reality itself may be fundamentally indeterminate until measured, implying a participatory universe where observation is not just passive, but an active player in shaping existence. This raises profound questions about whether reality is objective or if it depends, at least partly, on observation. Experiments continue to probe these questions, with quantum entanglement and delayed choice experiments pushing the boundaries of what we understand about cause and effect and the nature of reality. While these ideas can feel strange, they remind us how quantum theory invites us to expand our perspective. The observer, far from being a mere spectator, is woven deeply into the fabric of the quantum world, adding layers of mystery to the silent dance of particles and waves. As you listen quietly, allow yourself to rest in this gentle wonder, where reality and observation meet in a delicate balance, forever inviting us to explore further. Quantum mechanics reveals a universe where chance plays a central role, sparking long-standing debates about randomness and determinism. At the heart of this is the question: are the fundamental processes of nature truly random, or is there a hidden order beneath the apparent chaos? In classical physics, determinism reigned. If you knew the exact state of a system, you could predict its future perfectly. But quantum mechanics shook that certainty. Events at the quantum scale, like when a radioactive atom decays or where a particle appears on a screen, seem inherently probabilistic, governed by chance rather than strict laws. Some interpretations accept this fundamental randomness as a built-in feature of reality. The probabilities encoded in wave functions do not hide deeper certainty. They reflect true unpredictability. This randomness is not due to our ignorance, but is woven into the fabric of the quantum world itself. Others, however, seek a deterministic explanation behind the scenes. Hidden variable theories suggest that unknown factors might control outcomes, preserving a predictable universe at a deeper level. While intriguing, these theories face challenges from experiments, such as those testing Bell's inequalities, which place strong limits on hidden determinism. This tension between randomness and determinism remains a rich field of inquiry and philosophical reflection. It touches on ideas about free will, causality, and the nature of laws that govern the universe. As you relax and drift, consider this dance between order and chance, where the universe seems to balance unpredictability with underlying patterns, inviting endless curiosity about what lies beyond our current, quote, understanding. In the unfolding story of quantum mechanics, a new concept has emerged: quantum information. Unlike the classical information we use every day, which depends on bits that are either 0 or 1, quantum information is carried by quantum bits, or qubits, which can exist in multiple states at once. This property unlocks remarkable possibilities. Quantum information is not just about particles or waves, but about the ways they encode, transmit, and process data at the smallest scales. It reveals a new layer beneath physical reality, a framework where information itself behaves according to quantum rules, blending certainty with uncertainty. This idea has profound implications. It allows us to imagine computers that harness superposition and entanglement to perform calculations far beyond today's machines. It also promises new methods of secure communication, impossible to intercept without detection, thanks to the fragile nature of quantum states. More than a technology, quantum information suggests a fundamental shift in how we understand the universe. It points to a reality where information and matter are deeply intertwined, where the fabric of existence might be woven from patterns of information just as much as from particles and energy. As you settle into quiet rest, consider how this unseen information quietly flows through the universe, shaping everything from the tiniest atoms to the grandest cosmic structures. It is a gentle reminder of the deep, elegant complexity underlying all things, a mystery inviting us to look closer and wonder. Quantum mechanics asks us to reconsider ideas we once took for granted. In classical physics, objects have definite positions, paths, and speeds, predictable and certain. A ball rolls along the path, a planet orbits its star, and light travels as a wave. But at the quantum level, these intuitive notions begin to dissolve. Particles don't behave like tiny billiard balls anymore. Instead, they exist as probabilities, described by wave functions that spread across space. They can be in multiple states at once, a concept called superposition, challenging the idea that things must have a single, definite condition at any moment. The quantum world also reveals entanglement, a mysterious connection between particles that persists even when separated by vast distances. This defies classical ideas of locality, suggesting that information or influence can link particles faster than light, or at least in ways we cannot easily understand. Measurement itself becomes a puzzle. In quantum mechanics, observing a system doesn't simply reveal its state, it influences and even defines it. The famous wave function collapse implies that reality is not fully determined until measured, unsettling the classical belief in an objective, observer-independent world. These challenges force us to accept a universe governed by uncertainty and probability, where cause and effect are more subtle and intertwined than classical physics ever imagined. It is a quiet, profound shift, inviting wonder rather than certainty, curiosity rather than closure. As you listen softly, let these ideas settle gently, opening space for mystery and reflection on a universe far stranger and more beautiful than everyday experience suggests. Quantum mechanics gently pulls back the curtain on a world where certainty gives way to possibility. The idea that uncertainty is woven into the very fabric of reality invites us to rethink what we mean by knowing, being, and existence. At the smallest scales, reality does not present itself as a fixed, unchanging stage. Instead, it is a dynamic, unfolding mystery, where outcomes are not predetermined, but probabilistic. This challenges the classical view of a clockwork universe, perfectly ordered and predictable, revealing instead a cosmos alive with chance and potential. Philosophers and scientists alike have pondered what this means for our understanding of truth and knowledge. If the act of observation influences what becomes real, then the line between observer and observed blurs. Does reality exist independently of us, or is it in part shaped by our engagement with it? This uncertainty invites humility, a quiet acceptance that some questions may forever elude definitive answers. It opens space for wonder, for the beauty of the unknown, and for embracing the mystery that surrounds us. In this light, the universe feels less like a problem to solve and more like a story to experience, rich with nuance, depth, and subtlety. The uncertain dance of particles becomes a metaphor for the openness of existence itself, where unpredictability is not a flaw, but a feature of a living cosmos. As you drift in this gentle reflection, may you find peace in not knowing, and comfort in the quiet spaces between certainty and mystery. Beneath the familiar layers of quantum mechanics and general relativity lies a profound puzzle: how to reconcile these two pillars of modern physics into a single, harmonious framework. This quest is known as the search for quantum gravity, the elusive theory that unites the microscopic world of particles with the vast curvature of space-time. Quantum mechanics governs the realm of the very small, with particles behaving in probabilistic and wave-like ways. Meanwhile, general relativity describes gravity as the warping of space-time itself, shaping the motion of planets, stars, and galaxies. Yet, when these two theories are brought together, such as near black holes or during the earliest moments of the universe, they clash, revealing contradictions that challenge our deepest understanding. Scientists have proposed several approaches to bridge this divide. String theory suggests that the fundamental building blocks are tiny, vibrating strings, whose different modes create particles and forces, including gravity. Loop quantum gravity, another contender, attempts to quantize space-time itself, envisioning it as a woven fabric made of discrete loops. These theories remain incomplete and unproven, yet they open doors to new ways of thinking about space, time, and reality. Could space-time be granular rather than continuous? Might the universe have multiple dimensions beyond those we perceive? These questions beckon us to explore beyond current horizons. While answers remain distant, the search for quantum gravity highlights the remarkable depth and subtlety of nature's design. It reminds us that the universe is not yet fully known, inviting quiet curiosity and patient wonder. As you rest in this thought, let the mystery of unification cradle your mind, an infinite puzzle waiting, softly, in the quiet cosmos. Among the many ideas proposed to unite the forces of nature, string theory offers one of the most intriguing visions. Instead of viewing particles as tiny points, string theory suggests they are actually tiny, vibrating strands of energy, like microscopic loops or strings, each vibrating in its own unique way to create the particles and forces we observe. But string theory asks us to imagine something even stranger, that our familiar three-dimensional space might be only part of a larger, more complex reality. According to this theory, additional dimensions exist, hidden and curled up so tightly that they escape our everyday perception. These extra dimensions allow strings to vibrate in a multitude of ways, giving rise to the diverse particles and interactions in our universe. Without these hidden dimensions, the mathematics of string theory wouldn't hold together, and the elegant symmetry it offers would fade. While the idea of extra dimensions may seem like science fiction, it is a natural consequence of the theory's equations, beckoning us to expand our sense of space beyond what the eye can see. Physicists continue to explore these possibilities with great care and subtle experiments, seeking signs of these hidden dimensions in particle accelerators or the echoes of the early universe. String theory remains a beautiful and mysterious idea, one that stretches the imagination and hints at a universe far richer and deeper than our ordinary senses reveal. As you imagine these unseen dimensions unfolding gently beyond sight, let your mind wander softly through the quiet depths of possibility. Quantum field theory is the modern framework that blends quantum mechanics with special relativity, describing particles not as isolated points, but as excitations in underlying fields that fill all of space. Imagine invisible fields stretching everywhere, like a calm sea beneath the surface of reality. Particles arise as gentle ripples or waves in these fields, each with its own characteristics. This powerful approach explains how particles interact and transform, uniting electromagnetism and the nuclear forces into a coherent picture. Yet, despite its success, quantum field theory also reveals unexpected surprises known as anomalies. These subtle inconsistencies emerge when symmetries thought to hold perfectly in classical physics are gently broken at the quantum level. Anomalies have profound consequences, sometimes dictating which theories are physically possible and which are not. They can lead to new predictions or restrictions, guiding physicists toward deeper understanding. These phenomena remind us that the quantum world is delicate and full of subtle balances. Ongoing research probes these anomalies, using mathematical precision and experimental insights to reveal the fabric of the universe more clearly. Quantum field theory continues to evolve, shining light on the fundamental forces and particles, and opening pathways to new physics beyond the known. As you drift in thought, imagine these vast quantum fields gently humming beneath all things, their subtle anomalies weaving the complex tapestry of existence. Quantum biology is an emerging field, exploring how quantum phenomena, usually confined to the tiniest scales, might play surprising roles in living organisms. It suggests that life, at its core, may subtly tap into the strange rules of the quantum world. For example, photosynthesis, the process plants use to convert sunlight into energy, exhibits remarkable efficiency. Some studies indicate that quantum coherence, where particles exist in multiple states simultaneously, helps energy move through plant cells with minimal loss, almost like a perfectly choreographed dance. Similarly, certain birds seem to navigate using Earth's magnetic field through a quantum mechanism in their eyes, sensing magnetic directions via entangled electrons. This quantum compass allows them to migrate thousands of miles with stunning accuracy. Even our sense of smell might involve quantum tunneling, where particles pass through barriers in a way classical physics cannot fully explain, helping receptors detect odors more precisely. These hints don't suggest life is governed by quantum mechanics in a simple way, but reveal a delicate interplay where quantum effects may enhance biological functions. It's a quiet frontier of science, blending physics and biology in mysterious, elegant ways. As you relax, imagine these tiny quantum whispers within living cells, quietly supporting the processes that sustain life, weaving the fabric of existence with subtle quantum threads. Particle accelerators and detectors are the eyes and ears of modern quantum physics, allowing scientists to probe the tiniest building blocks of the universe. These massive machines accelerate particles, like protons or electrons, to near light speed, smashing them together to reveal what lies beneath ordinary matter. In the colossal tunnels of accelerators such as the Large Hadron Collider, collisions generate energies and conditions similar to those just moments after the Big Bang. This recreates the primordial environment where fundamental particles first emerged, giving us a glimpse into the universe's earliest moments. Detectors surrounding these collision points act like sophisticated cameras, capturing the fleeting traces of particles born from these high-energy impacts. From tracks of charged particles to bursts of energy, detectors record a rich tapestry of data. This data has led to groundbreaking discoveries, including the Higgs boson in 2012, confirming the mechanism that gives particles their mass. Yet, accelerators continue to push boundaries. hunting for new particles and forces beyond current knowledge. These experimental frontiers transform abstract quantum theories into tangible insights. They remind us that the invisible quantum world is not just imagination, but a reality we can explore, piece by piece. As you settle in, picture these great machines humbly peering into the fabric of existence, uncovering secrets that deepen our understanding while inviting peaceful wonder. Emerging quantum technologies promise to transform many aspects of our lives, ushering in a new era shaped by the strange rules of the quantum world. These innovations harness principles like superposition and entanglement to perform tasks impossible for classical devices. Quantum computers, for example, use quantum bits or qubits that can represent both 0 and 1 simultaneously. This parallelism allows them to solve certain complex problems exponentially faster than traditional computers, opening possibilities in cryptography, optimization, and simulation of molecules. Quantum sensors take advantage of extreme sensitivity to detect tiny changes in magnetic and electric fields, gravity, or time itself. They could revolutionize navigation, medical imaging, and even the search for underground resources with unprecedented precision. Secure communication methods, based on quantum cryptography, promise nearly unbreakable encryption by detecting any eavesdropping attempts through the fragile nature of quantum states. Although many quantum technologies remain in their infancy, ongoing research and experimentation bring them steadily closer to practical use. Their development represents not only a leap in capability, but also a gentle unfolding of the universe's deepest secrets. Imagine these emerging technologies as quiet threads weaving a new fabric of understanding and possibility, soft, complex, and full of wonder. As our quiet exploration of the quantum world comes to a close, we find ourselves lingering in a space between certainty and mystery. The tiniest parts of reality reveal a dance of probabilities and waves, of particles both here and everywhere. It's a realm where the familiar dissolves into the strange, inviting us to embrace the unknown. There is comfort in this gentle uncertainty, an open invitation to wonder, without needing all the answers. As you rest now, your mind weaving through the invisible patterns that shape everything, remember that this silent world will be waiting for you, patient and unchanging, whenever you return. So breathe deeply, let your thoughts soften, and allow the quiet hum of quantum mysteries to lull you toward peaceful sleep. And so, under the quiet stars, the story continues. Good night.